so I gave you back the exams. I graded out of 54. The high score is actually 53. I was going to put on the two most missed questions. There were two questions that I checked the answers. They were right, that students had a really hard time with. But I did not put them in today's lecture, so I'll probably bring them back at a later date to talk about. Why? Because we're starting with chemistry today. Now, you know I'm not a chemist, but I've taken years of chemistry, so here we go. We've already started talking about some things that we're talking about today. And since the scientific method is really important to me for this class, I introduced this before talking about scientific method. I'm going to talk about the scientific method again. So around 465 BC, Democritus, I have it spelled right in everything this time, came up with the idea of atoms. That is the Greek word for indestructible, saying that materials were made up of little tiny pieces. And if you cut small enough, you'll get to where you can't cut it anymore. That's the indestructible, indivisible piece. So these atoms, as hypothesized by Democritus, notice that's almost 500 years before Christ. So that's, it's a long time ago. He said that these things you can't break them into smaller pieces. Everything consists of them. You can't destroy them. You can't see them. Homogeneous. Homogeneous is a word that we should make sure we understand. Homogeneous means that they're the same everywhere you look. You don't have variations. If you have a gold atom, it's a gold atom. It's going to be the same everywhere. You do have different sizes and shapes depending on the type of material. So if you have a solid, he said, the solids, the atoms are little small pointy atoms, and liquid, they're big round circular atoms, or spherical atoms. So those were ideas put out long before the birth of Christ. A couple hundred years later, a big name came on the scene, Aristotle. And Aristotle did not believe that Democritus was right. Aristotle talked about the four elements that everything is made out of, and he didn't believe that they were atoms indivisible. He just said everything's made out of some amounts of earth, water, air, and fire. And since Aristotle was such a highly esteemed thinker, everybody said, well, Aristotle believes it. Who am I to disagree? If there is a consensus among the greatest thinkers in the world, how could I disagree? And so for 2,000 years, this is what people basically believed. So as we understand things now, because the great thinkers had a consensus one way, everybody went from a correct idea to an incorrect idea. Something we should think about now when people try to use the ad populum or what is it? The one for somebody that has prestige as arguments. Well, if Neil deGrasse Tyson believes it, you must believe it. No, that's an invalid argument. Doesn't mean it's wrong. It's more likely to be right if he believes it, but it's not a valid argument. Hello, Brittany. Here, have this piece of paper, Brittany. It's a piece of paper that tells you how much I appreciate you. I didn't hear her response, but I assume it was a thank you. Oh, there we go. Okay, come to around 1880. In the 1880s, John Dalton started doing some research with chemistry, and he noticed that in reactions, you have always this ratio of this type of atom to this type of atom when you have a certain reaction. That is, 5 grams of this to 7 grams of that. That's what I mean by this ratio. And so he said, well, this atom. I should be more clear in my words because this is shifting back to the atom idea of this element versus this element. So what's an element? An element is a material made of only one kind of atom. Of course, the definition of element couldn't have been that if you didn't believe in atoms. But one type of pure material and another type of pure material. So he said, I think this atom idea was a good idea. So started making a comeback for the atoms. And then we have J.J. Thomson, who around 1904 came up with what we call the plum pudding model. Why? Well, if we look at what Dalton did, he did experiments, and the experiments suggested that the Aristotelian model of earth, water, air, and fire was not sound. And so he changed his understanding because of results of experiments. Now we had J.J. Thomson, who was studying what we called cathode rays, some kind of ray that was coming out of the negative side of a vacuum tube. Let's just go with that and move on. And in studying these, he determined that there were electrons coming out of metals. And so he deduced, well, he observed something interesting. There are electrons coming out of metals. And so then he came up with a hypothesis. And by the way, almost everyone had the first 4 steps perfect for the test. I was really impressed with that. So a hypothesis to explain why electrons could come out of the metal, and he made the obvious hypothesis. There must be electrons in the metal since they're coming out of the metal. And so he proposed then that we have atoms, but the atoms are like plum pudding. You have a bowl of, I always think of it as oatmeal with raisins in it. And the oatmeal is the positive charge just spread out everywhere in the atom. And then the raisins are the electrons that are randomly distributed in that oatmeal so that you can have electrons come out. So that was the plum pudding model. And notice the date, about 1904. Now things move fairly rapidly from there until we get to our present understanding. So after the plum pudding model, we have 5 years later the planetary model, where under the guidance of Ernest Rutherford, Hans Geiger did experiments with gold foil. And remember, we talked about this before. He found that some of the alpha particles bounced back off of that gold foil. And if it was the plum pudding, if that was correct, you couldn't have had anything to make it bounce back. So this was a test of the plum pudding model that Rutherford proposed that the person in his lab do. Proposed to test a theory that had been pretty accepted in those 4 years. And so they were shocked. They knew right away this experiment disproved the theory. So what do you do if you disprove the theory? You go and you make a better theory because you have more information about what it's not. And so he came up with a planetary model, which this picture doesn't really do justice. It has the electrons orbiting the nucleus in circles like planets orbit the sun, except for we know that planets don't orbit the sun in circles, right? They're doing ellipses. Ellipses, I believe that's plural of ellipse. No, ellipses. Ellipses is the ... Then we have Niels Bohr. So once again, this is only 4 years different, 1909 to 1913. Niels Bohr came to work in Rutherford's lab. I have to point out he was a Danish physicist because, I'm going to go to Denmark this summer. I'm not going to see my Danish ancestor or relatives because we lost touch with them, but they were there. My uncle lived with them when he went to college. Anyway, so he went to work with Niels Bohr, and they realized right away for things like we're going to see here, although we won't understand the totality of it, came to determine that simply the planetary model couldn't be correct. There were lots of violations. Things like with planets orbiting the sun, there is no rule to tell you how far a planet can be from the sun. There's no rule to tell you how much energy the planet has as it orbits the sun. But in looking at the light that comes from gases, such as we're going to do in a few minutes, he said, well, there are only certain energies that the electrons can have. And so Bohr actually came up with what we call a quantum hypothesis. He said that the angular momentum is equal to some integer multiplied by a constant. So the electrons orbiting can only have an angular momentum that's 1 h bar or 2 h bar, that's what we call that symbol. and so on. Now, you don't have to know this equation. You're never going to use that equation. Just showing it as it was the first quantum idea that we have only certain angular momenta that the electrons can have as they're orbiting the nucleus. And he furthermore made a rule, it's just an ad hoc rule, that the electrons have a steady energy and can't just willy-nilly change their energies. And since they can't change their energies, then remember I said the planetary model has to be wrong because the electrons should fall into the nucleus in less than a billionth of a second as they lose energy. So he just said they can't lose energy. Hence, they can't fall into the nucleus. So he came up with some ideas that we now call quantum physics. So it was the first quantum model. And so it said that electrons have specific radii that they can orbit the nucleus in circles. But there's specific radii now with only certain energies and radii allowed. So that's 1913. Over the course of the next decade, physicists got really perturbed about the idea of where are the electrons in these atoms? And so they started studying more and more, trying to find them, and determined they couldn't locate them at all. So we had people who took different approaches. We have the people like Erwin Schrödinger, who took de Broglie's idea of a matter wave and said that we could treat the electrons as if they're waves. As long as the electron is moving, we could treat it as a wave. And using that wave idea, he came up with a quantum physics method using calculus, differential equations, to describe the motion of the electrons except for one thing. It doesn't tell you the velocity of the electron at all. It just tells you where you're likely to find it, where you're less likely to find it, and things like that. We had other people like Heisenberg who said, okay, let's just forget all about where the electrons are. Let's not worry about that. Let's simply measure the energy levels and work from there. And so he came up with a completely different method of doing quantum physics, but it gives exactly the same results. So two different approaches to the quantum model. Now, before I go to my next slide, I want to zoom in here. We've talked about this before, but it's important that we point it out because we're going into chemistry. Atoms are the basis of all chemistry. And so the atoms, as we understand it now, have a nucleus that is positively charged. What are the two types of particles in that nucleus? Protons and neutrons. What's the charge of a proton? Positive. Okay, now we just say positive. It's, plus 1 charge of an electron, or plus 1.602 times 10 to the minus 19 coulombs. That's the charge of a proton. Every proton is exactly identical to every other proton. You can't differentiate, this proton I'm going to date Bob. This one I'm going to date Marie. And I can follow them, I'll know which one's Bob and Marie. You can't tell the difference. The same is true of neutrons and of electrons. You can't distinguish them, they're all identical. So we have in the nucleus protons with a positive charge, neutrons that are essentially identical to protons but have a zero charge. Zero charge means they just don't interact with the electric force. And then orbiting that, we have electrons. Now, this picture shows the electrons as if they're doing circles. Inaccurate. They're not doing circles. But it's a useful model. A model is a way of talking about things. Now, back with Bohr believed it was correct, right? We don't anymore. But it's a useful way of talking about things. So we'll draw pictures like this for an atom. And in fact, you'll see a truncated, it only has the first 3 periods of the periodic table that has these drawn. And it emphasizes this isn't accurate. It's not what really is going on, but it's useful for helping us understand how chemical bonds work. So this picture just shows electrons with different radii, and those radii correspond to different energies. The ones farther away are not as tightly bound to the nucleus. The ones closer are. So that's the basic Bohr model. Now we get to the quantum model. Here's 2 pictures of the quantum model. This one here is more what you're used to seeing. a spherical distribution. And some atoms do have a spherical distribution. A lot of them do, but not all of them. So this here is another figure showing the distribution of the electrons. And you see it's nothing close to spherical. What do these shapes mean? It's where you're likely to find the electron if you go hunting. Don't know where the electrons are, but these are the places that it's high probability that you're going to find one. This one here just shows a spherical distribution. Like I said, there are some atoms that are like that with a spherical distribution, but it's fuzzy because we don't know where the electron is in there. We just know it's somewhere likely in that region. So with this quantum model, which was developed over the time from Bohr through around I usually say around 1930. I think the neutron was first hypothesized like in 1931. So before that, they didn't even have the idea of the neutron. But they noticed that there were some mass discrepancies, and so they went looking and found the neutron. This model says that the electrons have specific energy levels, and the energy levels are, well, we have the orbital shape corresponds to that SPD stuff. But you have only so many electrons that go in each energy. Now, if you think about energies, you might be wondering, how does that have anything to do with anything in chemistry? Chemistry is all about energies. If I take this ball and I let go, what happens? It falls. It's going to fall to the lowest energy available. So it's going to fall down and settle on the table here. If it rolls off the table, it goes down to the floor. Well, that's what we have for energies of electrons in an atom. There's different energy levels they can have. And so one might be the tabletop and one might be the floor. The lowest one they can reach we call the ground state. Because if I drop the ball, that's the lowest state you can get to is the ground. They're going to fall to the lowest available energy state. But you can only put 2 electrons in the ground state. So if you have something with, say, 5 electrons, the first 2 are going to go in the ground state. First 2 electrons that find that nucleus say, zoom, I'm going down to that ground state. But then the next 3 are like, the ground state's filled. I can't get in. So it has to go to the next higher energy state. So that'd be like putting them on the table. And you could put 6 on the table, and then you have to go to the next energy state. So we have these different energy states according to the quantum model. Now our first clicker question. Which of the following are incorrect statements about an... Oh, I didn't actually talk about this, so we'll talk about it as soon as you answer. This is checking what you know already. I believe it will only accept one answer. So even though it says which are, there's only one answer it will accept. So don't try to put in, oh, A, B, C, and D. You'll figure it out. It's down to you. There we go. Everyone that's here answered. 1, 5, 2, and 15 answered, so 7. All right, well, we have a lot of differences of opinion here, so let's look at these. Atoms have been around since the beginning of the universe. The understanding that we have of the Big Bang, which we clearly didn't talk about here, is that at the Big Bang, there was a lot of energy just in the form of radiation. A lot of energy, so high of energy that you couldn't form any particles. But then soon after, and we're talking just, fractions of a second later, it cooled enough that you could start forming protons. And at that point, that's what they mean by the beginning of the universe. Protons still make up the nucleus of about 90% of all of the atoms in the universe. So what element is just a proton? If you look back behind you, we have the periodic table of elements as designed by Mendeleev. And hydrogen, the first one, the top left, it's in that position because it has one proton in the nucleus. So hydrogen is 90% of all the atoms in the universe. Well, as things continued on and it cooled, you had collisions between protons, and you could get two protons to undergo a particle physics interaction that made one of the protons disappear and be replaced by an electron and a neutron and an electron antineutrino, if you care. And in that process, helium was built up. So about 90% of the atoms in the universe are helium. Okay, who's good at math? What's 10 plus 90? 100. We got to 100% of the atoms, and we only did hydrogen and helium. Everything beyond hydrogen and helium is a very minor constituent of the universe. And these atoms have been around ever since. So that's our understanding, that atoms have been very eternal. Now, I'll talk about alchemy in just a moment, and how alchemy tries to change that. Let's go to the next one. Atoms are mostly empty space. I didn't talk about this, but if you read in the textbook, it says that if we were to scale up an atom to be about the size of an average airport runway, it says 3 kilometers, that the nucleus would be about the size of a basketball. And then you have a few electrons, which have, as far as we know, no volume, whirling around in a cloud that's 3 kilometers across. That's mostly empty space. The vast, vast majority of an atom is empty space. So that was a true statement. Next one, atoms are perpetually moving. Well, yes. Yes, they are. If we were to get down to absolute zero, then in theory, we could have them stop, but the atoms are moving around. So that leaves the one that is incorrect. Atoms are manufactured in plants and in humans during pregnancy. During pregnancy, the mother's body is not creating atoms to form the baby. The mother's body is taking in nutrients, which have, at their core, atoms, and those atoms are then being built into the baby. So the baby is being created, but the atoms aren't. And we believe that atoms are eternal, can't create them or destroy them for the most part. And so, as the textbook mentions, I'm breathing. And each time I breathe out, millions of billions of atoms. Where do those atoms go? They spread out everywhere. Within a couple of years, those atoms will be equally distributed over the entire world. And some of us are going to breathe in that air, and the atoms that I exhaled will breathe into you, and your body will take those atoms and put them into cells in your body. And so atoms are constantly moving around, and I have atoms in me from probably every person that's ever lived on the earth. And you do too. Right? The atoms aren't tagged, and we can't say, oh yes, this one belonged to Napoleon. Dynamite. But we know that statistically, I have atoms from everybody who's ever lived in my body. Which is kind of creepy, but it's also kind of interesting. Okay, let's come back to the idea of manufacturing and talk about the difference in chemistry versus alchemy. Chemists are looking at how atoms interact and how they bond with something. Alchemists are largely interested in trying to, at least from my reading, trying to produce gold, trying to transmute elements. Now, when I was a child, like 6 or 7, I firmly believed that if you had something that was the color of gold and was metallic like gold, that you should be able to somehow transmute it into gold. There must be some magical way, and I didn't think magic, I thought physical, of doing that. It didn't help that I watched like the $1 Million Duck, that Disney movie where this guy's wife makes horrible, horrible applesauce, and the duck eats the applesauce and makes its eggs turn to gold. No? That's what alchemists were trying to do. And for the most part, that's not possible. But I have to give you the one way it is. High energy physics can do this. What is high energy physics? That's things like taking a proton and accelerating it. So we make particle accelerators, like the particle accelerator over there at CERN, or the Stanford Linear Accelerator, or it's now been put out of commission, but the particle accelerator up in Fermi Lab near Chicago. And you can take protons and make them go really, really fast and smash them into a nucleus, and sometimes they'll stay in the nucleus. And when you put a new proton in the nucleus, you change the element. You change it from one type to another. And so there are ways of doing this alchemy, but they're super expensive because of all the energy needed. Now, when we talk about radioactive materials are naturally doing this. You take uranium. The vast majority of uranium is uranium-238. What does that mean? Okay, so I'm going to write this down, uranium-238. There are two things that are important here. Uranium has the symbol U. It's uranium if it has the right number of protons. So you can look back there at the periodic table of elements and locate U. It's the last one that's in bold, that's black. It's the last one that's naturally occurring. If it's black, that means that it occurs in nature. If it's not black, it only occurs because men have been able to make it with their particle accelerators. So if you look at U, it has a number up in the right corner. What's that number? 92. That number 92 is the element number. Number of protons, and it's called the atomic number. So any atom that has 92 protons in its nucleus is uranium. What's the other thing that we find in the nucleus of atoms? Neutrons. That 238 is what we call the atomic mass. And that tells us the total number of protons plus neutrons. So we write that right here. So uranium-238, the U and the 92 are completely redundant. If you know it has 92 protons, you know it's uranium. The 238 then tells us about the number of neutrons. So if we have 238 things in the nucleus, and 92 of them are protons, and all the rest are neutrons, you can do the math. How many neutrons are there? Okay, I heard somebody at least answer. I should.
146.
Okay, so there are 146 neutrons in that nucleus. Notice there's a lot more neutrons than there are protons. On the other hand, with hydrogen, there was one proton and no neutrons for the normal hydrogen. Okay, so I was on the transmutation. Uranium-238 is radioactive. Periodically, it will give off a particle. Most often, that particle is 2 protons and 2 neutrons very tightly bound together. We call that 2 protons and 2 neutrons an alpha particle. But if you look at the periodic table, what element has 2 protons? Helium. Helium. See, 2 up in the top right.
Oh, I saw them.
So helium has, that was the period number. Yeah. So helium has 2 protons, so the thing that's coming out of the nucleus is a helium nucleus because it had 2 protons. But if uranium loses 2 protons, it started with 92, loses 2 protons, how many are left? Really hard math, 90. If you look at the table, what element is it when it has 90 protons?
90 is not up. Yes. That thing.
TH. And the TH here is thorium, not thallium. Aren't you glad to know that there's thorium and thallium? And one of them's TH and one of them's not?
I said thadium.
Okay, so it becomes a new element. And as it goes through giving off these alpha particles, it will go through and become, radon, or radium, radon, polonium, and then finally lead. And so the lead we have comes from the transmutation, the radioactive decay of uranium. So there is that way the elements do change. But we don't manufacture them. We can smash things together sometimes. So talking about the elements, we have, this says 115. That table back there agrees with it. But as of last year, well, it's within the last 6 months, there are 4 newly accepted elements. And so the number here is not right anymore. And 90 are found naturally in nature. The rest of them only made by humans. We've talked about the proton. We talked about in the past, right? I talked about how to get electricity in because we have the protons, the electrons, important things in electricity, important things in chemistry. Protons are about 1,800 times more massive than electrons. So when you measure the mass of an atom, you don't worry about counting up the electrons for the most part. Now we do at some level, but at the beginning level, we don't worry about counting up the electrons. We just count up the protons. And, there's another particle that has essentially the same mass, the neutrons. Neutrons have the same mass as a proton, almost exactly, not perfectly, but almost exactly, just no charge. And so when we talk about the mass of an atom, we just add the protons and neutrons. That's why the number of protons plus neutrons we call the atomic mass. Electrons, all the electrons are identical to each other. They have a really tiny mass. Of course, we've learned likes repel, so electrons repel each other just like protons repel each other. And that's what keeps atoms from getting too close. So we've talked about this before. The reason I don't just fall through the floor is because the atoms are keeping me from pushing them apart. There's a picture in the textbook. I think it's a mother holding a child. I was reading on my phone last night, so it's a little hard to tell. But it says they're not really touching. It seems like they're touching, but they're not. What you have is the electrons are repelling other electrons so they can get close, but they never touch. For all practical senses, you can say they're touching, but the electrons are pushing them apart so they never actually touch. When somebody puts a sword through a watermelon, realistically, the sword no electron in the sword touched an electron in the watermelon. It just forced them to move apart. Okay, the word isotopes. You probably all watched The Simpsons enough to know that the name of their baseball team is the Isotopes, right? Nope. Isotope is a word for elements that have different numbers of neutrons but the same number of protons. So I talked about uranium-238. There is also uranium-235. Uranium-235 is the element that they use to make bombs or power plants. And so uranium-235 is a different isotope of uranium. It has 3 less neutrons, but the same number of protons. We have common isotopes, the book points out carbon, like 99% of carbon is carbon-12. If you look at the C back there, the C is the second row on the right side, the second one. The C has 6 protons. So if 99% has 6 neutrons, what would you suspect its total mass to be? 12. Now, a very small percentage, like 1%, has 13 things in the nucleus, which means it has 7 neutrons. And so if you look at the mass of the carbon up there, it tells you the mass. I think it's bottom center. So Brittany, you're closest. What does it say bottom center under the C? 12.0 what? Okay, so it's 12.0108. That 12.0108 is telling us the true mass of a collection of carbon atoms. And it's measured in units we call atomic mass units, which has an abbreviation of just U. And I'll have the definition of the atomic mass unit on a coming up slide. So when you read that periodic table, it tells you the average mass of a collection of atoms that has different isotopes, different numbers of neutrons based on how nature distributed them. So here it is. The atomic mass unit is 1.661 times 10 to the minus 24 grams. Of course, grams is not the SI unit for mass, it's kilograms. So this one here is in the standard unit. 1.661 times 10 to the minus 27 kilograms is one atomic mass unit. And so if I have one atom of carbon, if it's carbon 12, it's going to be 12 times this for its mass. Okay, now our second clicker question. I do not want to install software updates in the middle of class. Thank you, computer. The atomic number of an element matches the number of what? So notice it's the atomic number. Are you in the wrong? There we go. Okay, so we have 8, 1, 5 with its invisible, and that must be 1. So the atomic number, the majority of people said protons in the nucleus of an atom. Actually, this is pretty much a straight knowledge, so there's not much point saying, why'd you answer it? Because it was correct. That is the correct answer. The atomic number is the number of protons in the nucleus. Now, one person said electrons in a neutral atom. If you have a neutral atom, what does it mean for it to be neutral? Net charge is 0, no charge. So if I have protons are positive and electrons are negative and they have the same magnitude, they have to have the same number, right? If you have 6 protons in a carbon atom, if it's neutral, it also has to have 6 electrons. So by a transitive, using the definition of the neutral atom, B was also correct. What was that? So that means that C was the correct answer. Yeah, I didn't even notice C. Thinking. Okay, so both of them were correct because although it technically means A, a neutral atom is going to have the same number of electrons. Okay, so now the periodic table. The textbook emphasizes, don't memorize it, which is funny because what did you do in high school chemistry class if you took it? First thing you did was memorize it. I mean, my son's taking high school chemistry right now. And so, he comes home, I got to memorize all these. Help me learn them. And, I don't have them all memorized either. And so I kind of appreciate this not telling me that I have to have them memorized. So what is that table? Now, that's not the only periodic table that's ever been devised, but it's the one that we use today. Actually, I should stay up front instead of walk to the back. That table is separating the elements based on their chemical properties. And what Mendeleev did was he looked at properties like, which things will form a bond with chlorine? And all the ones that form a bond with chlorine, he put in a group. Which ones will form a bond with nitrogen? Puts them in a group. And so he went through and he grouped them based on their chemical properties as well as on their masses. And he came up with an arrangement of everything in one column has similar chemical properties. So if you look up there, H is the first thing in the first column. Down below is Li, lithium. Lithium has very similar properties to hydrogen. Down below that's sodium, potassium. K is potassium. Rubidium, cesium, francium. Those all have similar chemical properties. They'll form the same types of bonds. And so that's why he put them in that column together. And then he tried to put it so the top one's the lightest and it gets progressively heavier as you go down. So the columns are called the groups. And the groups should be similar. Of special importance are the groups on the ends. So this group right here, I don't know why I keep losing my... Those are called the noble gases. They're noble gases because they don't need no one. They don't form bonds with things. They just hang out all alone. To make them form a bond, you have to excite them and do crazy things to them. So those are the noble gases, things that are really unreactive. The next column is called the halogens. So this column here
is that the stuff we need to know?
Yeah, we do need to know this stuff. And the halogens, it tells us in our textbook, means that they're the salt-making atoms. You guys know table salt, right? And most people know the chemical formula for table salt. What is that? NaCl. Na is sodium. Sodium is in the first column. Cl is chlorine. It's in the halogens because it's salt-making. The salts, well, what we often think of as salts, are combinations of elements in the first group, which is called the alkalis, because they make ash, the alkalis and the halogens. So while sodium chloride is the one that people are most familiar with, sometimes you'll get something that's an iodized salt. If it's iodized, that means you have iodine, that's I. Where's I on that chart?
53.
Okay, it's 2 below chlorine, was the key I'm looking for. 2 below chlorine, it's in the halogens. You can replace the chlorine with iodine and make sodium iodide. Or you could have brominated salt, where you have sodium bromide. There's still salts. So those are the halogens. Then there's a vocabulary word that I learned last night as I was preparing. These here were called the chalogens. I had never heard of that before. Anyone else heard of that in their life? Okay, let's not worry. Oh, you had, Valerie. Oh, my goodness. Do you remember what it means? Because I don't. I don't remember what that even means. I was like, what? I think they misspelled it, but no, it's the wrong column. Yeah. So we have those over here. These here are called the alkalis. And the ones next to it are the alkali earths. What's special about these? The kinds of chemicals they form. What do we have? Does anybody remember from your reading what? I was going to put my thumb over it. I guess I can't. Here. Anybody remember from your reading what that means?
Metal.
Metals. The vast majority.
You can see it on your.
I know. I mean, it was pretty transparent. The vast majority of our elements are metals. Now, the metals that we're used to talking about are in the middle part. So what we usually think of as classical metals are these things in here. Right, things like aluminum, Ag is silver, Au is gold, Cu is copper, Fe is iron. Right, the things that we tend to think of as metals are in that center region. And so those are actually called the transition metals. Here are the new elements, just in case you want to know. They go in those places. They had placeholder names. You have things like unseptunium, it's unseptium. That means 117. Or, unpentium, 115. Those were not very imaginative names. Those were placeholder names because they figured there should be something that has 117 protons in the nucleus. And now they know, and so they've called it tennessine. You might guess the origin for at least some of these names. Where you suppose nihonium was discovered? Okay, maybe you don't know the name Nihon for a country name. The Nihonjin call their country Nihon. We call it Japan. So nihonium was discovered in Japan, in Nihon. Moscovium. Yeah, it wasn't Moscow, Idaho. It's Moscow, Russia. Right? Tennessee. Probably Oak Ridge Laboratory in Tennessee, right? And Oganesson is another Russian one. You don't have to know the names, but it's interesting to look at the names. A lot of these are man-made, like, Neptunium and Plutonium, the same order as the first two predicted and then discovered planets. Americium, clearly from America. CM, curium. BK, berkelium, because they discovered it at Berkeley. CF, californium, because they also discovered it at Berkeley, just like americium. I think the vast majority of these down here were discovered at UC Berkeley. You have fermium. ES is Einsteinium. MD is Mendeleevium. Mendeleev is the person who came up with the idea of the periodic table that we have. Nobelium, because Alfred Nobel gives a lot of money to people in science. Lawrencium, because it's Lawrence Livermore National Laboratory. Lawrence is the last name of one of the founders of the laboratory. Okay, so that's our periodic table. We have vertical columns or groups that have similar chemical properties. Horizontally, each row is called a period. So here it has the groups and periods marked. Last thing I'm going to talk about is the sizes. And then we'll have a clicker question on this and go. The sizes of elements is not what you might think. Since you start at the left, you have 1. Go to the right, 2. Go down one row, 3, 4, 5, 6, 7, 8, 9. The numbers are constantly increasing as you go. The number of things in the nucleus increases, you go over and down. And yet for the sizes, the largest size elements are found in group 1. And the sizes tend to get smaller as you go across. So if you were to compare rubidium with xenon, the rubidium atom, even though it has a lot less protons in it and a lot less electrons, is actually a larger atom.
How big an atom is? Do you stick it under something?
That's a very good question. The best they can do is the scanning electron microscope. So which atom is larger, a lithium atom or a fluorine? Notice they're on the same row here. The one's on the left and one's on the right. Okay. Class is up, so please hurry quickly. Hurry quickly. I mean, answer quickly. Hurry. You know, English, my first language. I will give it only about 5 more seconds here because we got to get going. No. Since we had more than 3, you should all actually have it anyway because everybody answered the previous ones. So even if you didn't get on this one, it shouldn't hurt your grade. So we had 651. What was the key to answering this? Which side is larger in size? The left. So this one here is larger. Which one has more mass? The one to the right. Now, there will be a homework assignment due Wednesday. It'll be based purely on today's lecture, so it won't have many problems because just today's lecture.